to cover the first part of tectonics for our class. I hope that we actually covered some of this in class. So if that's true, if we covered some of these slides in class, what you should do is you should fast forward through what we covered in class and only take notes on the parts that we didn't quite get to. So I'm going to go ahead and jump in to the beginning because I want to make sure everything gets covered just in case it doesn't. So plate tectonics. When we're talking about plate tectonics, we are not talking about continental drift. Continental drift was an old theory put forth by Alfred Wegener that is actually a failed theory. His concept in that theory was that the continents themselves, these sections here, like Africa or South America here, float on the oceanic crust, which is actually brown in this picture. Not really brown in real life, but it looks brown here. Now, what we actually have is the theory of plate tectonics. That is our best understanding currently with all of the evidence we have so far. This is the best description we have currently going. It's the most well supported theory that we have to date. In this theory, the entire outer shell of the Earth is made up of these slabs of rock that have boundaries. That's what this turquoise color is. So basically, instead of being like the shell of an egg that's one uniform surface, the Earth is made up of different sections, like puzzle pieces. At these boundaries, where plates come together or pulled apart, we have different landforms being created. For example, this one here that's in the ocean and coming up through here in the Atlantic Ocean is a divergent boundary where new rock is made. Now, in this boundary here, the Mediterranean, we have a convergent boundary where plates are actually moving toward one another, eventually going to close up the Mediterranean Sea, and it will be no more. So Africa is slowly smashing up into Europe. So plate tectonics is a geological theory that the outer layer of the Earth is a dynamic layer, which means it moves, it changes its shape over time, which is made up of many huge slabs of rock called tectonic plates. Here you see a tectonic plate, and actually location, let me see, I believe right about here or here, I'm not sure which, is actually a very deep part of the ocean called the Mariana Trench, but we'll talk about that in a bit. Or I think, no, we'll talk about it a bit. So these large sections of rock, called plates, move. Some places they are crumbled up into one another. Some places they are recycled, which is called subduction, or subducted back into the Earth. Now, big misconception people have with the Earth is that it's liquid inside. It's very, very hot, and so people assume that there's just magma flowing inside the Earth. That's not true. This pinkish red portion is actually a solid. It's very, very hot, and so it has movement to it that mimics a liquid, but it's not quite right. We call it a plasticky solid, which means it's solid, but it's also able to deform without breaking. Now, this diagram is showing two lithospheric plates. A lithospheric plate is made up of ocean rock on top of very upper part of the mantle, the upper mantle. Or over here, it's made up of a piece of, again, the upper part of the mantle. This side, it has a covering of continental crust over top of it. Now, what happens is when we have oceanic crust coming in contact with continental crust, we have a subduction happening here. This denser oceanic crust will actually go into the Earth. Remember, that's called subduction. When that happens, the ocean sediment rock, because of the excess salts that are in that rock, it'll actually cause isolated melting. That's what these little worm Cheeto looking like things are supposed to be representing, and it will cause a big magma chamber. If that magma chamber builds up enough magma, it will actually turn into a volcano. Now here is an image of the Andes Mountains here. It's just showing a volcanic created mountain range. Doesn't look much like a volcano though, but it is. Okay, sorry, hit the wrong button there. Okay, back to where I was supposed to be going. Alright, so other places rock can be moving apart. And when it moves apart, it can create new rock and oceanic mountain ranges. Now, kind of already talked about that, but here's the Atlantic Ocean again. And here, this map is actually colored specifically due to age. So newer rock is red, yellow and oranges are getting older, green is older, and then blue here in the ocean is the oldest rock we have in this section. We have some older rock in the ocean, but the rock of the ocean is actually newer rock. Rock of the continent tends to be older rock, and that has to do with the fact that oceanic rock is more dense. It's primarily made up of a rock called basalt or another type of rock called gabbro, and because it's a little bit more dense, when it slams into the continent, not here but in different locations, like here would be a prime example of where it slams into the continent, the oceanic crust will tend to subduct into the earth, and so we end up having the continents staying up on the surface more often than subducting or being recycled. So we have much older rock, millions to billions of years old rock here on the continents, while in the ocean, the oldest rock, I believe, I'm not sure on this date, is about 200 million years old. Now here is a diagram sort of showing what a divergent boundary, these boundaries where one plate here, another plate here are moving apart from one another. That's what these arrows are indicating. And here we have the mountain range. Now it's not a very tall mountain range, but it's a mountain range nonetheless. Now here we don't have melting because of subduction like this plate will eventually do. But instead we have what's called decompressional melting happening right here. Because these plates are being pulled apart or they're being pushed apart, whichever theory you want to resign yourself to, there's less pressure from the crust pushing on the asthenosphere here. Less pressure, molecules have more room to move around. If they have more room to expand, because the asthenosphere is so hot, it's actually going to allow it to melt. So we get another isolated location near the crust or in the crust where we have melted rock. This melted rock forms here. As it forms in this mid-ocean ridge, the rocks push apart some more. We get more new rock, and then we have this conveyor belt motion of rocks moving away very, very slowly from the mid-ocean ridge. So what we tend to do is have new rock here, while we've got older rock here further away from the mid-ocean ridge. Now in places of subduction, this is a convergent boundary, we're going to have something called an oceanic trench. These are the deepest places in our ocean. All of this movement of the outer layer of the Earth, these sections called the lithosphere, is caused by internal heat inside the Earth. So here the asthenosphere, remember it's not a liquid, it's a solid, but it's a plasticky solid that allows it to deform, and because of that, the heat directly from the core here heats actually the mesosphere, which is not actually shown here, which moves in a convection flow. Convection flows, remember, should only travel in a liquid or a gas, but because the asthenosphere and the mesosphere are so hot, they kind of deform. Now they move very, very slowly because they are a solid. They don't move like air currents move. But the mesosphere will transfer its heat energy up to the asthenosphere, which is about as thick as this layer. And as the asthenosphere is moving in these cyclonic motions, it's going to drag these lithospheric plates apart from one another And this zone, it's actually going to bring them together and cause subduction or mountain building processes, depending what crusts are coming together. So the center of the Earth is very, 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 very hot. The core is about as hot as the surface of the sun, about 10,000 degrees hot. So this heat transfer is well enough energy to be able to make the movement due to convection currents. So our planet has a few layers, and each layer was formed billions of years ago due to density differences. Most of the dense materials sunk inward to the core, while the least dense material is here on the shell of this outside of our planet. Now, the crust is actually really thin when you look at the whole entirety of the Earth. The crust of the Earth, if it was the size of an apple, so if our planet, we shrunk it down to the size of an apple, the crust thickness would be about the thickness of the skin on that apple. So when we categorize layers of the Earth, we categorize it into two categories. We do it in physical layers and chemical layers. So here in your notes, you're going to write this down, the blue part, obviously. Physical layers, also known as, that's what AKA stands for, also known as mechanical layers, are way we divide up the layers of the Earth based on how they move or interact with each other, as well as their physical states of matter. Now we also have a way to designate them the chemical layers. They're divided based on the chemical composition of the layers. This is probably what you learned in elementary. This is the different breakdown that you're used to, our mantle, core, and crust. And what we're going to do is we're going to diagram both our chemical and physical layers. On your notes, you have two circles. One circle has the label physical chemical, and the other one has, one has physical mechanical, and the other one has chemical layers. On your notes, it looks just like this. Alright, so what we're going to do is we're going to start on the physical layer side first. And we're actually going to make the different layers here. So what I'm going to do is I'm going to start with the core of the Earth. Draw a circle in the middle of your Earth that's about that big. Then draw yourself another circle that's about that big. Now they don't need to be perfect because for this class you actually don't need to know the exact proportions of all the layers of the Earth. So it's not perfect, it's going to be okay. Draw yourself another circle like this. So now we've got it broken up in the middle circle, another circle, this big section, and this section. Now, let's go ahead and label these. Now, the center layer is the inner core. It is a solid, so let me make sure you indicate that on there. It's actually an iron nickel, more iron than it is nickel in the center. Now, this is the hottest layer. It should be a liquid. If it was on the surface, it would be. However, because of all of these other layers pushing down on it, creating pressure, because gravity's pulling everything in, actually forces it in to be a solid. That's just because to be able to become a liquid, molecules have to be able to expand outward. That's how we transfer from a solid to a liquid form. Molecules start to vibrate, they spread out, and they are able to become liquid, more fluid. However, all this weight, we're not getting a solid or a liquid here, we're getting a solid, even though it is hotter than all of the other layers combined, or not combined, but all of the other layers above it. Alright, this next layer is the outer core. It is the only liquid, well, it's the only fully liquid layer in the Earth. We do have isolated sections in the crust where we have some liquid magma, but as far as we're talking about entire layers, the outer core is the only liquid layer. It's hot enough where it can be a liquid under the amount of pressure it's under. So basically, it's liquid, but cooler than the inner core just because there's not as much pressure from the overlying rock upon it. This next layer is called the mesosphere. Mesosphere is just meso actually means middle. So it's the layer in the middle. You'll find when we talk about the atmosphere, there's also a mesosphere in the atmosphere. And guess what? It's also in the middle. So this layer has more volume. So there's more matter in the mesosphere than all the other layers. So it's basically the biggest layer of the Earth. Now our next layer is the asthenosphere. It is a solid. Now in both the mesosphere and the asthenosphere, we've got convection currents flowing, transferring heat energy from the core to these other layers. Now it's due to the movement of these convection flows that our outside layer here moves, creates mountain ranges, creates volcanoes. Well, most volcanoes anyway. Now the outermost layer is called the lithosphere. Litho, I think, actually means layer of rock or something like that. I actually don't remember, but it's something like that. Now it's a solid. It does have isolated sections of liquid rock in it called magma or lava, depending on where it's located at. But this is the section of rock that's what we call brittle. It's made up of the upper part of the upper mantle. So the upper part of the, or what would be the oceanosphere, but it's not the oceanosphere, and the crust, the outside layer that you walk on. Now those layers are, like I said, brittle, which means they're solid enough, they're cool enough that when you try to deform them, they tend to break and they tend to snap. These breakages are actually faults. So you guys should have learned about faults last year, and I think most of you probably did. But that's the section of rock that breaks. Now that can happen anywhere in the entire crust, but it happens more frequently, more often, where plate boundaries are, where these huge slabs of rock actually come together, pull apart, or slide past one another. Alright, so now we're going to move on to the chemical layers. We're going to go ahead and note those on your on your notes. Okay, so we've got the chemical layers up here. These are the ones you're more familiar with. Let's go ahead and label these. Draw yourself a circle in the middle. This is going to represent our core. I'm actually not going to split this up into inner core and outer core. I'm just going to split it up into one. Now the chemical layers, they are not divided on how they move and interact in the Earth. They're divided basically on what they're composed of. So that's why we have the core as one thing, because the core is made primarily of metals. It's got iron and nickel for its main composition. Now the section here that was the asthenosphere, the mesosphere, and a small part of the lithosphere was this section, and we're going to be calling that the mantle. Now this outer layer, which is actually probably a little too thick on this diagram to be the outer layer on this, is what we're going to be calling the crust. So let's go ahead and label those layers. Okay, so we got the core in the middle, mantle in this section, and the crust. Now, unfortunately, when we start talking about the lithospheric plates and all the theory of plate tectonics, we're going to be referencing the asthenosphere and the mesosphere collectively often as the mantle, which is just confusing. It's geology. We don't always be very strict on our naming usage and correct vocabulary. So I'm going to be using the word mantle a lot when I should be using asthenosphere or the mesosphere, or maybe the upper mantle to mean the asthenosphere, because that's the terminology you're going to see on many tests instead of asthenosphere. Okay. Here's the diagram from the presentation file. We've got, they call this the rigid layer. This is collectively the asthenosphere. We've got, in this drawing specifically, we have the crust of the continent. We've got the bottom of the lithosphere, which is the upper part of the upper mantle. We've got oceanic crust here. Now I can tell it's oceanic crust even if the water was removed because it's so thin. Thin crust is automatically going to be oceanic crust. Oceanic crust is just not as thick as the continental crust on average. And here's the continental crust. I can obviously tell because it's big and bulky. And then here again is the oceanic crust. Alright, the physical layers of the Earth, we've got the inner core, which is the hottest layer. Now, while you're taking notes, if you haven't figured this out yet, you should be pausing if I'm going too fast for you, which I will be because I'm just reading this off and not giving you time to actually write things down. But every time you see blue, you should be pausing, writing it down. Anyway, the inner core, the hottest layer, it's also solid iron and nickel. Despite the heat and intense pressures, do not allow this inner core to be anything but a solid. So it's so hot that it glows, but it's still going to be a solid ball. So the outer core is the only completely molten layer in the entire Earth. And by molten, I mean liquid layer. Heat and pressure conditions allow the iron-nickel rich layer to actually be a liquid. And what's interesting about the outer layer and the outer core and the inner core is the interactions between the two. Because one is liquid and able to spin around, it generates a magnetic field, which we already talked about, hopefully. You guys remember that. But this is what's generating the magnetic field of the Earth. Right, the mesosphere is the largest layer by volume. Lower mantle is another name we call it by. Not very accurately, but that is what we call it by. And basically heat transfers directly from the core, creating a convective flow. So solid layer, it flows, however, more like a putty than an actual solid. The asthenosphere, which we sometimes call the upper mantle instead, also has convective flows, just like the mesosphere, which transfers this heat energy, but because it's directly touching the lithosphere, this is what's going to cause plate motion. This is what's going to cause the plates to drag apart or be force ramming together. This is what's creating landforms, building up landforms, on the surface of the Earth. So this is going to be creating volcanoes. This is what's been created island arcs. Not all islands, but some island arcs. Well, all island arcs. Not all islands are island arcs. Continental arcs, like off the coast of South America. Islands like Japan, an island arc just like Japan. Now the solid plasticky layer, it moves kind of like a putty. Lithosphere, this is what you're walking on. It counts the crust and the upper part of the upper mantle. So it's the outermost layer of the Earth. Like I said, it's made up of the crust and the uppermost part of the mantle. The layer is dotted with magma, which is liquid rock, near some plate boundaries and hot spots, which we haven't talked about yet, but we will. It's a real rigid, solid layer that fractures, and when it fractures, it sends waves through the Earth. This is what we call earthquakes. It is the layer that's responsible for creating mountains, islands, and continental arcs. And again, not all islands, but, well, we'll talk about it. Alright, so the crust is the top section of lithosphere. And we have basically two types of crust, continental crust and oceanic crust. The continental crust, pretty obvious here, but it's the crust of the continent. It is the least dense layer, which is very important, actually, to remember. Mainly made up of granite rock. The thickness is about 30 to 50 kilometers thick. The oldest rocks exist on the continents. The oldest ones so far are 4.4 billion years old, and they're located in Australia. Now, the oceanic crust is again, the rock of the ocean. These aren't hard names, actually. It's geology. We tend to name things for what they are. Luckily for most of us here. The oceanic crust is more dense than the continental crust, so it actually, when they come together, it will sink into the earth. It's mainly made up of rocks of basalt and gabbro, as I said before, and most rock is less than 20 million years old. The average thickness is only 5 to 10 kilometers thick. Now, lithosphere is not made up of one large outer shell like that of an egg. Instead, it's broken up into sections. These are called lithospheric plates. Now, plate boundaries is where these sections come together. It's where they meet. The lithosphere is made up of large sections where they meet are called plate boundaries. This map showing different plate boundaries all around the world. Now, up in the Arctic Circle, you notice there's not really a plate boundary. It's because they're up there. We just have no idea where they are exactly because we don't have enough instruments up there giving us detailed information to be able to figure it out. But everywhere else in the world, we pretty much figured out at least a guess of where these boundaries lie. Some of these boundaries were like, I'm not so sure. But other ones were much more sure of exactly what those boundaries are. Now, if you look at this map, you should be able to know these little triangles and some of these little dots. Green lines with spikes on them. Some of these are just lines. All of this stuff on this map means something. If you look here, these little sort of step lines, that's called a spreading ridge offset by transform faults. So basically, this is the mid-ocean ridge, what we're looking at here. They're spreading centers, and these sliding sections are transform faults where rock is moving side to side. Here, we have subduction zones, places where this plate moving in this direction is actually moving and dropping down into the earth, being recycled right underneath South America. If you look, right where this location of these spikes are heading towards into the earth, you have a pattern of triangles. So what are those triangles? Let's look at the key. Right here. Those are volcanoes. So here's an example of a place where rock is being subducted into the earth, and then we have volcanoes popping up along that entire plate boundary. Same thing here. We've got a subduction zone, a bunch of volcanoes. Now, we have weird places with isolated polka dots, which are called hotspots. And we've also got volcanoes appearing at those hotspot locations as well. And we'll talk about what hotspots are and what we think creates those. Alright, now what I want you to do now is you're going to label your map with each of the 15 plate names. So right here, North American, Juan de Fuca, Caribbean, Pacific, Nazca, all these different names of the plates. I might not be able to pronounce this one, Scotia. The other ones you should be able to pronounce. These are places where you probably should know where these plates are, just based by basic geography. So what we're going to do is we're going to go through and we're going to name each one of these because you have to know the names of all the different plates. Only 15 of them, so it's not that big a deal. And most of them you should know because right here, if you didn't look at the key and not know it, you could probably guess that that's something to do with Australia, and that is, it's the Australian plate. So we're going to go ahead and name these. Make sure you're naming them on your map along with me. Okay, here we are. My stuff's kind of primitive, so I am using Microsoft Paint to be able to label all of these. Alright, so the first thing we're going to go through is we're going to label each one of these these plates, lithospheric plates. Alright, the first plate we're going to name is the one where you live. This is the North American plate. Pretty easy to remember that one. Alright, next. This one's a little bit different. but if you had a multiple choice test, you could probably pick it out. It's Eurasian plate. A lot of people like to laugh at that one. They're like, "You're an Asian." Yeah, I've heard that joke. It's not funny after you hear it 100 times. All right, next one is the African plate. I'm going to jump backwards and I'm going to come back to the South American plate. Right here, this might be kind of small in yours, so you might want to try to either write small or write it somewhere out here and then have an arrow delineating that this is a different plate. This is the, oh, I don't know how to spell it, Caribbean. Okay, I'm going to cheat and look down below. Apparently there's only one R. Caribbean plate. Maybe I'll just leave off plate because there's no room for that. Alright, this small one over here is called the Cocos plate. That one's a little bit weird. Maybe you don't know that one because that one's not really too geographical. I just made up a new word. Nazca, probably should be able to figure that one out if you've memorized the word Nazca. This one down here, this small one, Scotia plate. Up here, this weird shaped one that causes all the volcanoes in the Cascade Range is called the Juan de Fuca. Not the other way. Fuca. Watch your language. Juan de Fuca plate. Right there. And that would probably be one that you label out in the ocean and put an arrow to. Now this huge plate that's actually mirrored here, and then it continues over here, so we're going to label it in two places so we know what it is the Pacific plate. So I'm going to label it here, and I'm going to label it here. Alright, so we got the North American plate. We pretend this is just still one. This is still the North American plate. We got Alaska. So maybe we'll put it up here so you know. North American plate. Alright, let's go ahead and type this one in. Philippine plate. Philippine. I think that's how you spell it. Plate. Alright, this one down here is the Antarctic plate. This is the Arabian Peninsula. So this is the Arabian plate. This one right here is, I don't know, India. So it's the Indian plate. So honestly, studying these should be pretty easy because it's your basic geography. If you know your continents, you're going to get most of these plates. If you know your oceans, one ocean, it's going to really help. This one is your Australian plate. Wait, there's no either. Australian plate. And I think we got all 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I think I missed one. Okay, no, there are 15 there. Okay, we're good. So make sure you have all those. You will be tested on those. You will have to be able to write them in the right locations for the quiz. Alright, so plates push into one another and they can be either recycled back into the earth, which is called subduction again. But if there's a place where earth is removed, there must be a place where earth is renewed. So let's say if something's being recycled or subducted, if we're eating away crust, we've got to have locations where crust is made. And that is what we call sea floor spreading. Sea floor spreading are spreading centers. This is where new rock is being created. Now, at this distance, it doesn't look like a mountain range here in the ocean, but it does. It creates what we call the mid-ocean ridge. Mid-ocean ridge are spreading centers where new rock is being created and the plates are getting bigger in those locations. Here, as we saw before, this is another one of those maps. It's not temperature. It looks like temperature, but it's not. This is showing new rock and older rock. Now, if you were to look at this Atlantic Ocean ridge here, and you were to look at this, the Nazca Plate and the Cocos Plate, just looking at the map, what would you say, which one is actually spreading faster? Which one is creating new rock faster? Now remember, red signifies new rock, blue is old rock. So here's the question again. Which spreading center, this one here on the Cocos or the Nazca, doesn't matter which one, or the mid-ocean ridge in the Atlantic Ocean, which ridge is spreading faster? And think, how can you tell? Alright, so here you can see that the new rock is a very small range, and then it gets older and older and older as you move away from the ridge here. This new rock section is very large. So since this huge section of rock is much larger, but it's the same age as this rock, we can tell these spreading centers are spreading a lot faster. So we're getting movement moving out this way, movement moving out this way. This part, Mexico, is actually being shoved sort of towards Florida, while this Atlantic isn't pushing as hard. So the Atlantic Ocean is a spreading center. It is getting bigger, but it's slowing down. While this section, the Nazca and the Cocoa Plate, is spreading faster, getting bigger. So seafloor spreading, let's note what that is. Seafloor spreading, basically it creates new rock at spreading centers, or moors, we like to call it in geology. Moor stands for mid-ocean ridge. Or also continental rift valleys. So very rarely, we'll actually have a spreading center start to appear in the middle of a continent. Since the continents are so thick, it's actually going to stretch that continent out. So we're going to have a lower area. That's what we call a rift valley, because it's being pulled apart, and it's thinning and thinning and thinning, volcanic action happening, until eventually it will become oceanic floor, but that takes a very long time. So where plates pull apart, pressure is being released. So at these locations, we actually have something called decompressional melting. That's what's causing isolated magma at those locations, decompressional melting. The overlying crust is being removed. There's less pressure pushing on the asthenosphere in that location, and we're going to have melting, allowing magma to rise up and erupt out of volcanoes. So upwelled magma breaches the surface and creates new rock at that location. Mid-ocean ridges are spreading centers, where seafloor spreading is occurring. A moor, or mid-ocean ridge, is a long mountain range connecting all of the world's oceans. Every single one of the world's oceans has this mountain range running through it. Now you're going to learn in geography that some other mountain range is the longest mountain range in the world. It's because they're ignoring this mountain range. This mountain range is actually by far the longest mountain range in the world, because it goes all the way from the Atlantic around the Antarctic plate up into the Pacific in many different locations, and so it's just massive. It's very, very, very long. As new crust is created, these ridges, it pushes old rock out of the way toward recycling zones called oceanic trenches. Here is an image of an oceanic trench. So right here, we've got a mid-ocean ridge. In the Atlantic, I actually don't have any trenches, so we're not going to look at that. But here in the Pacific Ocean, there are a lot of oceanic trenches, one right off the coast of Alaska. So this deep section here, that is deep ocean right there, that's a trench. Alright, so we're going to go ahead and diagram seafloor spreading. Alright, here is a block diagram. Basically, block diagram means like a 3D drawing. what I want you to do is I want you to draw in this slab here. Now the mid-ocean ridge, it's a mountain range, but it's only a mountain range because the asthenosphere here is risen up and it's kind of pushing it up from underneath. We've got isolated decompressional melting here, and then we have new rock being created in this sort of cleft in between the slabs of rock that are being pulled outward. Don't forget to draw in the arrows. Don't forget to draw in the labels. That's very important on a diagram. So we've got the arrows, we've got stuff going up here, pushing along. This asthenosphere is actually moving in an upward direction, and then it actually pulls this way as it moves along, pulling these slabs apart. Decompression melting happens, and we've got magma. Boom. Go away. Alright, so plate boundaries. Boundaries are locations where different plates come together. The way they come together and what type of rock it is will determine the landforms created at those locations. If a subduction occurs, where this is where again one plate moves under another into the earth, if subduction occurs, will be determined by the type of crust on top of the lithosphere that's actually coming together. If it's oceanic or continental or oceanic, it's going to make a big difference. Now, if you haven't taken a break while taking notes yet, you're trying to cram this all in one night, you shouldn't be doing that. You should have already taken a break by now and come back to this maybe on a different day. Don't cram it all in one day. Anyway, let's go ahead and skip to the next slide. Convergent boundaries are when plates are moving into one another. So this creates, I should say creates, but it says this creates island arcs, which is what happens when two oceanic plates converging together. It also creates volcanic continental arcs. This is when an oceanic and a continental plate comes together. Or we can have a situation like the Himalayan mountains, where two non-volcanic slabs are coming together and merging. So large earthquakes can happen at any one of these boundaries. They can also have small earthquakes, but they do have the potential to have very large earthquakes. So examples of specific locations created by this type of boundary would be the Andes Mountains in South America. That's here along this whole entire boundary. This is a continental arc. Notice the curving of the land. This is what we call the continental arc. We've got subduction plate of this oceanic plate here going underneath the continental, causing melting, creating this entire range of mountains. Now another example, Cascade Mountains in the northeastern United States. That's these mountains that run through the northern California all the way up through Oregon and Washington. Mount Hood is an example of this. Again, volcanic mountains. What we have here, sorry about that. What we have here is, again, oceanic, the Juan de Fuca plate, actually specifically, merging underneath, melting due to subduction, and creating this volcanic range on the North American plate. Other examples we have is the Himalayan mountain range in Tibet. These are actually non-volcanic. There are isolated volcanoes here. For the most part, we don't have volcanoes in this section. So here's an example of those types of mountains. Now these happen mostly by crumpling plates together. And here's a map of where the Himalayan mountains are located next to Tibet, the place that China pretends doesn't exist and is not real. And then also every oceanic trench around the entire world is an example of a convergent boundary. including the deepest part, which is the Mariana Trench in the Pacific East of the Philippines. Now, the Mariana Trench is so deep, it's nearly 11,000 meters deep, which is about 36,000 feet. That's actually deeper in the earth than Mount Everest is tall above the sea level. So Mount Everest, the tallest mountain in the world, Mariana Trench actually goes deeper down into a trench than it is tall. So example of those trenches, here we already saw this one. This is the Aleutian Trench. It's right next to Alaska, the Aleutian Chain Islands of Alaska. So here's the trench here. And then the Marianas Trench here. We got a globe showing where we are in the world. Here's China. Here's Japan. An island arc, if you can see that arcing thing created by this convergent boundary. And then the Marianas Trench right here. This is the deepest place in the entire world. Alright, basic diagrams. I kind of covered this bottom one because I didn't really like that diagram very much. This one's a little bit more accurate. So what I want you to do is I want you to add these three diagrams. Now, I said when plates are coming together, if one goes under and melts, it's going to determine what plate it's going to be determined by what's on top of the plate. Right here we have an oceanic covered lithospheric plate where we got thinner oceanic crust saturated with salts, subducts into the ground. Those salts change the melting point of the rocks here. Isolated melting turns into a range of volcanic mountains, a continental arc here. This diagram showing two oceanic plates coming together. Same thing, we got isolated melting, but now instead of having a continental arc, we have islands forming here in an island arc. This would be an example of Japan. Japan's a perfect example of this. The Philippines are a perfect example of this. Now the last diagram we have here is of two continental crusts coming together. We will sometime have subduction here because of old oceanic crust that's attached to this continental crust that's not at a boundary, so it'll sort of subduct. But what happens is we get a continental crust, they're about the same density, neither of them wants to give, they're both very, very old, so we don't have any subduction here, and we get a crumpling of mountains, similar, and a high plateau, similar to the Himalayan mountains. This is why the Tibetan plateau is so high. It's because these crumpling, actually, it's because India is smashing into Asia. That's just literally what's happening. India is just completely still plowing into the continent. Oops, that did not go where I wanted it to go. There we go. So a divergent boundary is where plates are moving apart or diverging from one another. On land, this is going to create a rift valley. In the ocean, it's going to create a mid-ocean ridge with a cleft in the middle. This is where new rock is created. Remember, this is from seafloor spreading. This is what this is called. Melting occurs here because of decompressional melting. Instead of subduction, we've got decompressional melting. So these boundaries will typically have small earthquakes. Rarely they'll have a 4.0 earthquake. That would be a big earthquake for these type of boundaries. So example of these type of boundaries around the world is the East African Rift Valley and mid-ocean ridges. So here we've got a map of the East African Rift Valley. Basically, we have a very rare place in the world where the continent's being pulled apart. We have a new boundary forming. There's not a boundary here yet, officially, but a new boundary forming. Eventually, this will start to fill with lakes, which it already is. That's going to thin more, and ocean water is going to start to fill in, and eventually it will be all oceanic rock, and all this other rock will have split this way, this rock will have split that way, and this chunk of Africa will break off. Well, not like into the ocean, but it will just move off, I should say, more accurately. Here's a photograph of what that looks like in some locations. Now this kind of just looks like a valley, but if you know what you're looking for, you can find it. And it will also be dotted with basaltic volcanoes, shield volcanoes. Here again, mid-ocean ridge, we've seen this several times. You have that cleft going down the middle. You've got transform boundaries in between the sections where it doesn't quite line up right, and you have new rock being created at these centers. Photograph of this, oh my goodness. Photograph of this is actually in your notes. This is kind of what this looks like. This is cleft in the rock. Sometimes they're much wider than this. Sometimes they're just small. Sometimes they actually look closed up, more like this one here. This is kind of weird. It's got a lot of pillow basalt, but we're not teaching geology here, so we're not going to go into that. Alright, basic diagram. This is what we're going to be looking at for the mid-ocean ridge. We've got decompression and melting going on. We've got this moving off. The asthenosphere is actually moving in this direction this way, moving in this direction this way, pulling these two plates apart. Some scientists will argue that the convergent boundaries that actually cause subduction to happen is what actually pulls these down. So they call it slab pull instead of slab push. This would be an example of pushing if we were saying that this is new magmas pushing these rocks apart. But slab pull is the theory that subduction is actually pulling these slabs of rock apart from one another. We don't really know which one it is. We just know they move apart. Now, here's a diagram. You don't have to put both these in here, but you might want to for fun. I don't know. This would be an example of what continental rift valleys are going to be looking like. So remember, the continent is much thicker than oceanic crust. This is a closer diagram, but what happens, we start to have basaltic lava coming out. We have these volcanoes. It starts to push these plates apart, or maybe they're being pulled apart. We don't know. And eventually we start getting this kind of step-like topography that's symmetrical, creating a rift valley. Eventually you start getting lakes and oceans filling it in, and then eventually it becomes oceanic crust and becomes a mid-ocean ridge, just like we have here. Transform boundaries. Transform boundaries are plates move in sideways motions. They're going past one another instead of into one another or apart from one another. They're like cars on the freeway. They're going in opposite directions. So no volcanoes here because one, plates are not pulling apart, so we don't have decompression or melting, and we have no subduction. So we have no chance of subducted crust changing the boiling point of the rock and causing things to melt. So these boundaries, because it's rock grinding against rock, they have the potential to have very large earthquakes. California, this is why California has so many earthquakes, because it's on a massive transform boundary. Examples of these kind of faults around the world is San Andreas Fault in California and the Alpine Fault in New Zealand. So here's maps of that. San Andreas Fault goes from about, now this is a convergent boundary right here, and then here is where the fault starts, where it's a transform fault. It goes almost through the entire state of California. Now these leave scars on the surface of the earth. This is San Andreas Fault right here. You can actually see where the fault line is, where one plate is going one direction. Actually, I think this plate's coming this direction, and this plate is moving off in the other direction. Now here's the fault in New Zealand. And this one, New Zealand has a lot of old volcanic rocks, and so it's actually harder to see this fault line. So it's actually kind of ripping the volcanic, extinct volcanoes apart here. And then we've got the transform fault here. All right, diagram of this. What we've got is we've got land moving in opposite directions, as in this diagram. So basically it's just moving in this way, and this is where we're going to get that fault scarp. Basically the plates don't just move perfectly side to side, but they're actually usually going to be like one's going to grind up on top of one another a little bit, and so we'll get that fault scarp motion right there. Now we also have transform boundaries at the mid-ocean ridge. So mid-ocean ridge, as we said before, these are spreading centers. This is where new rocks being made. However, not the entire mid-ocean ridge is lined up. Look here. You've got mid-ocean ridge, shifts over, mid-ocean ridge section, shifts over. These little shifty parts right here and right here, rock is traveling in this direction, but on this plate, it's moving in this direction. So you notice how it says transform fault, plate side past, right here. This one section right here, we've got transform boundaries. This rock is moving in this way. This rock is moving this way. So eventually, once it gets here, these rocks are moving in the same direction. So isolated sections in between divergent boundaries of the mid-ocean ridge, we have also transform boundaries. Alright, this is where we're going to end. I know it's a long video, a lot of homework. I hope we can get more lecture done in class more often. It'll be much better for all of our sanity. But we're going to do this activity in class. So this is the end of this video. We'll come back to class on Tuesday and we will work on this together.